one-dimensional situation on the lattice. Okay, this is just a comment. And even for a 3 plus one-dimensional system, the spiral is still relevant. Okay, and this spiral structure was first conjectured by these Russian people, and so sometimes this form of the condensate is called a DGR ansatz. Okay, but anyway, even for a 3 plus one-dimensional system, energetically, this state can be the ground state. Okay, energetically most favored. And the reason is very simple, very easy to understand. Okay, let's think about the quasi-particle dispersion relation. Okay, I mean the dispersion relation of fermions on top of this condensate. Okay, amazingly you can write down the dispersion relation, and then this is what you find. So here you have mass term, okay, mass of fermion, and here this is the wave number of this. Okay, so here you have Q, wave number, instead of chemical potential mu. Okay, in 1 plus 1 dimensional case, the rotation is characterized by chemical potential, but 3 plus 1 dimensions, this is not necessarily the chemical potential, because okay, so this elimination of chemical potential is no longer possible for 3 plus 1 dimensions. So this is a variational parameter. Okay, but the point is that okay, here you have minus Q. Okay, plus Q and minus Q, but plus Q is very massive, so you can forget about that. But anyway, the point is here you have minus Q also. And then if M is large and Q is large, then this mass effect can be compensated by the presence of the wave number. Okay, so naturally in the vacuum, large mass is favored, but as I said, at finite density, usually the smaller mass is favored. Okay. But here, you don't have to have small mass to have a big density. But okay, that mass effect can be cancelled by big wave number, and then you can have big density with large mass. Okay, this is very non-trivial. But this is possible with this condensate, very special form of condensate. And this implies that energetically most favored wave number should be given by something around the fermion mass. Okay? And this is indeed the case. This is some very simple model calculation. And indeed, this is the behavior of the wave number as a function of temperature and chemical potential. And this behavior is actually almost the same as this behavior. Okay? This is the chiral condensate as a mass, okay? Dynamical mass. So here and here, okay? So here you have the inhomogeneous phases, and in homogeneous phases, the wave number is something non-zero, but this behavior is obviously correlated to the behavior of the dynamical mass. And here you see the region of the inhomogeneous condensate without the vector interaction. And as I said, with vector interaction, the critical point is easily washed out. Okay, but for inhomogeneous phases, even with vector interaction, that is demonstrated by this blue region. Okay, so this is rather enhanced. Okay, the region is enlarged, but not washed out. Okay, so the critical point is not really robust against the presence of the vector interaction, while the inhomogeneous states are insensitive to the strength of the vector interaction. So in this sense, I must say that in inhomogeneous phases must be more robust speculation rather than yes.
I vaguely remember that this DGR instability only becomes visible when the number of fermion flavors is 10,000. So
yes.
Maybe that's at nu equals 0.
That is okay. That is a very good point. Okay, this is based on the perturbative QCD calculation, and in fact, so this type of the phenomena can this is a matter of the competition between this phenomena and color superconductivity. And if you have infinitely large number of the colors, then the color superconductivity is gone, and also the fermion screening effect is gone. Okay, and then the very strong forward scattering remains non-vanishingly, and that is the mechanism to favor this condensate. Okay, but that is the case only at asymptotically high density. Okay, in high density, such perturbative consideration makes sense. But now I'm talking about the intermediate density region, especially near the first order phase boundary. Okay, and near this first order phase boundary, as I demonstrated, so in this picture I showed this morning, the potential becomes very shallow. Okay, so this is the typical behavior of the potential. What? Oh yeah, yes. Okay, so this is a very typical behavior of the potential, and so because the potential is such shallow, okay, the energy gain coming from the cancellation between M and Q, that can easily overcome. Okay, and that is the reason why the inhomogeneous state appears just in the vicinity of the first order phase boundary. Okay, but it doesn't mean that the inhomogeneous phase needs first order phase boundary. Okay, even when the first order phase boundary is gone, the inhomogeneous phase still remains. Okay, and well, yes, and this inhomogeneous phase reminds us of a very old story in nuclear physics. That is P-wave pion condensation. Okay, this is a very old story. Proposed by these people and in 70s. Okay, and lots of nuclear physicists have been working on that stuff. And so, okay, so people say that this possibility was excluded by the experiment, but still this is a possible scenario, I must say. Okay, the P-wave pion condensation is exactly the same as chiral spiral. Okay, actually, you see, these are psi bar psi and psi bar gamma phi psi. They are nothing but the sigma condensate and pi zero condensate. Okay, and this type of condensation was actually speculated in the context of nuclear physics, and this was called P-wave pion condensation. Okay, the P-wave means inhomogeneous. Okay, so this is indeed inhomogeneous, and so this was actually investigated by this type of diagrammatic analysis. So this is quite analogous to the investigation in quark matter. But anyway, what happened is the following. Okay, so this is the interaction of nucleons and pions. Okay, but in nuclear matter, the pion exchange potential or the interaction between nucleon and pion, that is already the effective description. And to describe the very short-range interaction, you have to introduce some point-like interaction term. Okay? That is lambda omega parameters. Okay? And so these short-range interactions should be constrained by experimental data. And what is most important in this context is this interaction term. Okay? Coupling to the spin and isospin degrees of freedom. Okay? And this coupling constant can be inferred from the experiment of the Gamow-Terra giant resonance. That is a giant resonance associated with the oscillation of the spin and isospin degrees of freedom. Okay, and then this G prime was measured in the experiment, and this G prime was big. Okay, it turned out to be a big, and then so this effect. Okay, this effect of the instability was killed by the largeness of this coefficient. Okay, that was the conventional story about the P-wave pion condensation. But actually, some people are still investigating this issue, and they say that. So, okay, some people say that still the P-wave pion condensation is possible around the density twice of the normal nuclear matter density. Okay. Anyway. So this is not really yet, the situation is not yet settled. Okay? But anyway, so this is quite analogous and suggestive, I must say. And so the lesson from nuclear physics that we can take is the following. Okay? If you have this kind of interaction, this is against the formation of spiral. Okay? So we must also, in the context of quark matter, we have to take account of the effect of this type of effective interaction. That is, in the relativistic language, nothing but the actual vector interaction like this, okay? So there are lots of discussions about the effect of the vector-in-vector interaction. But then what is the effect of actual vector interaction? But this is actually very difficult to think about. Why? Because there is no mean field level contribution, okay? Even on the mean field level, the vector interaction has some effect. That is, the zeroth component of the vector is nothing but density, okay? So at finite density, even in the mean field level, you have some finite and very big contribution from the vector-vector interaction. But actual vector has nothing in the mean field level. So you have to go to the higher order contributions to take account of this effect, okay? So some non-perturbative method is really necessary. And so for that purpose, actually recently, I took holographic QCD model to investigate this issue. Okay, so in my remaining 15 minutes, so let me explain my recent work with my student Pablo Morales. So he's a master course student, but he's a very nice student. And actually, so we published a peer review recently. So if you want to have a good postdoc, then just wait for another 4 years or something until he graduates from my group, okay? Yeah, he's a very nice person. So, so this is the phase diagram from the Sakai-Sugimoto model. So this was first drawn by these people, Bergman, in 2007. And here you have the first order phase transition of deconfinement. And so this is completely consistent with the phase diagram of coconic matter, right? So here you have a straight line of the deconfinement phase transition and density onset here, okay? This is a confined phase and this is confined phase at finite density. But what is non-trivial is that you can draw another line corresponding to the chiral symmetry restoration, okay? So this information was missing in the consideration of the coconic matter. But this is of course, the chiral symmetry dynamics must be something very interesting, of course, okay? And so what is very interesting in the Sakai-Sugimoto model is that recently by these people, actually this is I think the Taiwanese group, and so by this, thanks to these people, it was known that the Sakai-Sugimoto model has inhomogeneous state, the spatially modulated region here. So this spatial modulation was partly discovered by these people, Oguri and Park. And so this part, the complete understanding was made by these people in Taiwan. Okay. And so, so everything is quite consistent with the conjectured QCD phase diagram, right? And so the Sakai-Sugimoto model is a very powerful tool, okay? But I don't have enough time to explain what the Sakai-Sugimoto model is. So just let me keep on the very intuitive level, okay? And I think that tomorrow you can hear more about the holographic technique by the lecture, in the lecture by Professor Kumar. Okay. Anyway, the point is that, okay, actually it is very easy to understand this first order phase transition, okay, deconfinement phase transition. This you can identify from the condition that, the most important feature in the Sakai-Sugimoto model is that this model doesn't have superparticles, okay? The superparticles are dropped by the condition of the compactification of the extra dimension, okay? That is denoted by x4, okay? This is not a Euclidean time, but this is some extra dimension, okay? Extra coordinate. And so this extra coordinate is compactified with antiperiodic boundary condition for fermions such that fermions are massive, okay? And so if you look at the dynamics, below this the scale characterized by this period, okay, period of this circle, that is nothing but the Caruso-Klein mass. Then the superparticles do not enter again, okay? So they are completely decoupled, and so the degrees of freedom you are looking at is exactly the same as QCD, okay, or group, Okay? So the gluonic reduced field only. And so this is the important point. But of course, at finite temperature, you also know that along the Euclidean time, so this must be also compactified, and this period is characterized by the temperature inverse, right? And then the point is the following. Okay, in the confined phase, in the confined phase, in the confined phase and in the deconfined phase, the load of this x4 and the Euclidean time tau, so these loads are flipped, okay, switched each other. Okay? So this geometry actually describes the confined phase, and this geometry describes the deconfined phase. That you can explicitly confirm by computing the Wilson line expectation value. Okay? And then the point is that there must be some phase transition, and that phase transition can be identified by the point where the energy or action of this geometry and the action of this geometry becomes identical. Okay, and the question is when it happens. Obviously, it happens when this the period becomes exactly the same as this period. Okay, then so this geometry and this geometry, they have their completely how to say the dual to each other, and so obviously the action has the same value. Okay, with this geometry and with this geometry. Okay, and in such a way you can easily identify the deconfinement temperature. Okay, that is given by the Holographic mass. Okay, and in this way, so you can easily identify this. But this information, chiral symmetry, this comes from a completely different physics. Okay? That comes from the flavor brain embedded here, and so this is D8 and D8 bar, and so this corresponds to the left-handed particles and right-handed particles, and if they are connected, then this indicates the spontaneous breaking of chiral symmetry, and usually this doesn't have such cusp. But at finite density, you have a cusp because you have the density source here, okay, introduced here, corresponding to the barium density. And alternatively, you can introduce density from the quark density, I mean some stringy contribution from this part. But you can show that the barium density introduced by this density source here has a lower energy. Okay, that was demonstrated. That was explicitly confirmed by Bergman. But anyway, so this part of this situation is a bit complicated to analyze. Okay, but the chiral symmetric phase is more trivial. Okay, in this case, the left-handed particle and right-handed particle, they do not talk to each other, and this configuration is simply straight. Okay, so you don't have to solve this non-trivial configuration. Okay, in this case, you have to solve this by solving the equation of motion. That is very non-trivial problem, especially in the presence of density source. But here, you can forget anything about that, and this is simply a trivial dynamics. Okay, and so this is very easy to think about that, and then. In fact, the Sakai-Sugimoto model is a very nice model, and so you can get the chiral magnetic effect very easily. Okay, so this is action to describe the flavor sector. So I don't have enough time to explain everything about the notations, but anyway, so this is so-called DBI action, and so if you expand this in terms of F, the leading order is of course FF, and that is a conventional action to describe QED or gauge sectors, right? And this is a more non-trivial generalization of the conventional action of the gauge field, okay, including some metric. Okay. Anyway, so here, so this describes the gauge field, and here you can introduce the magnetic field B, okay, or the vector potential corresponding to the magnetic field B, okay, and also some mesonic particles. And the important point is that, so in this model, it is crucially important to introduce trans-Simon action, okay, to describe finite density system, or the chiral magnetic effect. Of course, the chiral magnetic effect comes from the topological effect. So it is essentially important to introduce Chern-Simons action, or the density actually comes from Chern-Simons action in this model, and that is quite suggestive because, as I said, in 1 plus 1 dimensions, the density terms appear as a Wess-Zumino-Witten term. Okay, the density has an anomaly origin in 1 plus 1, and so this is not 1 plus 1, but even with a higher dimensions than ordinary Minkowski, but still the density comes from some anomalous term. Okay, this is very suggestive. Anyway, so from this expression you can simplify this problem into this form. Okay, so now you have finite chemical potential, that is the zeroth component of the gauge field. So you have to keep a 0, and also you have to keep a 3. Okay, the third component of the gauge potential, because you expect to have the current. Okay, and this 3 is a direction along which you impose a magnetic field. Okay, and then from this action you can solve the equations of motion, and this is a constant of the motion. Okay, and then this is the equation, the solution of the equations of motion, and from this you can write down the asymptotic solutions for A3 and A0. Okay, and then interestingly, okay, this coefficient. So this is actually the dual or conjugate to A3. That means this is actually the current, and this current is as expected from the chiral magnetic effect, exactly given by the magnetic field times chemical potential mu. Okay, so this is nothing but the chiral magnetic effect, and also here in the same way the A0 has this the constant of motion rho here, and so because the conjugate variable to A0 or the chemical potential is density, so this is nothing but density. Okay. So in this way, you have the topological current. Okay, and what is very interesting is that you can introduce perturbations to this the gauge field F. Okay, the field strength tensor F alpha beta. Alpha beta means this is not only mu nu, but also this alpha takes not only 1 to 4 but also 5. Okay, because now I'm working on higher dimensions. Okay. And then you can introduce some perturbation. And then you can find instability at finite momentum k. Okay? This is obviously the realization of the inhomogeneous state. Okay? And so in this way, you can find this spatially modulated phase. Okay? So now I'm working in the state with the chiral symmetry, the restored chiral symmetry. That means I'm not talking about this region, but I'm talking about this region. Okay? And then, so you can find the instability, and that was found by Oguri and Park. But what I did was I introduced the magnetic field, and I found that this instability region, okay, this region corresponds to this region, okay, here, okay, this region, and this region is significantly reduced by the introduction of the magnetic field here. So this is a result without magnetic field, and so here, if the magnetic field is 1.5 in some arbitrary unit in this model, then so the inhomogeneous region is appear only in this part. Okay, so the inhomogeneity is becomes less and less favored if the magnetic field becomes stronger and stronger. This is very surprising, right? Because okay, in the conventional understanding, if the magnetic field is strong, the system must have a dimensional reduction, and so you can expect more spirals in effective 1+1 dimensional system. However, what happens is completely opposite to this naive expectation. Okay, and then what is the interpretation for this result? The most reasonable interpretation should be the following. Okay, if I apply the magnetic field, I have chiral magnetic and chiral separation effect. That means actually this current is not only the vector current but also the actual current. Okay, and then naturally, so this type of interaction is induced by the presence of the finite density and the finite magnetic field. okay, even on the mean field level, right? And so this interaction is strengthened by the topological effect. And according to the nuclear physics wisdom, such kind of axial vector current must reduce the inhomogeneous phase of P wave condensation, okay? And so you have less spirals. And so this is in favor for the conventional scenario in nuclear physics, right? So this is a very surprising result, and I was really excited about this finding. And so this is actually, so also technical details you can find in the paper with Pablo Marles. So this is, because this is a letter, so this is only 5 pages, so you can easily read this paper. So if you are interested in, so please look at this paper. Okay, so anyway, so it's time to finish my lecture. So my concluding messages are the following, okay? So the phase diagram research has a lot of applications of various techniques such as lattice QCD, holographic QCD models, or effective model approach. Anyway, but the important point is that there is no all-round tool, okay? Even lattice QCD simulation has a weakness, okay? A very serious problem of the complex determinant, fermionic determinant, and also the holographic QCD model is very useful, but it is not exactly QCD, but it requires a large number of QCD, so the dynamics might be completely different from QCD itself, depending on the problem you are looking at, okay? So many things are still waiting for explanation, okay? The magnetic inhibition or inverse magnetic catalysis might be one of the examples. I must say that my scenario, magnetic inhibition, should be the answer, but you may oppose that, of course. And so your fresh thoughts are always welcome. Okay? So thank you very much for your attention.
Thanks for Kenji's 3 very interesting lectures. Questions? In your holographic analysis sort of says that your previous magnetic influence on the condensate actually was that has missed some effective interaction by the XO company.
Well, okay, my idea is actually you don't have to use a holographic technique, but okay, the point is following. The point is, so this interaction might be very important to think about the inhomogeneous space, okay? But nobody has ever considered this problem. Because
in your first analysis, this term was left out as well.
Well, okay, so in holographic QCD, everything should be contained, okay?
No,
of course,
your previous mean field.
right, you're right, okay? So the point is that if you have finite density and if you have finite magnetic field, you have topological current. That means you have something finite even on the mean field level, okay? So actually, you can apply this idea to the Navier-Naraszine model or any conventional effective model approach, okay? If you have so some students, and if the students get interested in that, then so this is, I think, a very interesting program. But anyway, so I demonstrated this idea using holographic QCD model, and indeed, I get something in favor for the conventional nuclear physics wisdom. Okay? So that can be tested by more conventional model like NJL by introducing this term and topological current. Okay?
More questions?
Can you make talk about the mathematical field influence on temperature of the confinement, deconfinement phase transition? Because in your lecture you are just talking about the magnetic effect on the calosymmetry breaking, some calosymmetry restoration phase transition. How about the confinement, deconfinement?
That is a very interesting question. Okay? Or in other words, the question is whether it is possible or not to have the confinement purely induced by the magnetic field. Okay? Nobody knows the answer, and